Okay. So yeah, I also was given a talk, Monsoons and Biogeochemical Responses. I've taken the liberty to interpret it in my own way. And the time given was 20 minutes originally, but now it's 30 minutes, so I'll talk real slow. So Peter blitzed through tons of stuff on monsoon dynamics. I'm going to try to bring it down to the ocean and basically try to make one point, that the Hasselmann is working on a daily time scale where the ocean is integrating the atmospheric forcing. And the biology and biochemistry is also working on a daily time scale to integrate the ocean physics. So when we run the model, obviously we are putting the forcing either coupled or forced ocean, whatever. So the model is integrating everything, but it's the way we look at it that can be different in terms of either understanding the biases or using the models to understand the biological response to the physics. So I'll explain what I mean by that. So to start with, this is just showing the upper level winds and the monsoon trough and the lower level winds for the boreal summer and boreal winter seasons. The classic thinking on how we think about ocean dynamics and biogeochemistry ecosystem response has been to basically focus on the dramatic changes in the winds or the kind of stuff that Amala was talking about in terms of the differences in the freshwater forcing and the physics, oxygen minimum zones, or the local and remote forcing via the waves. There are tons of papers which have looked at all aspects of the physics, and now there is more and more papers looking at biogeochemistry and ecosystems. Obviously, the Pacific gets most of the attention because that's where the signal is large and there is a lot of data. But the Indian Ocean, surprisingly, is getting much more attention than the tropical Atlantic now, for example, especially for biogeochemistry and ecosystems. So the tack I will take is to think about the monsoon impacts on biogeochemistry and ecosystems. It's better to go into the time scales at which the monsoon actually works, like the intraseasonal time scales that Peter Webster was talking about. So that might allow us to think a little bit more on the details of the physics forcing of the biogeochemistry and ecosystems. So monsoon, he didn't mention explicitly onset and withdrawal, etc. He focused a little bit on the ITCZ. So I will look at those and see how the ocean is integrating. And considering the unique nature of the Indian Ocean, Amala used this terminology that I also like very much, the flushing time scale. I think the entire Indian Ocean has a flushing time scale, which should be manifest in biogeochemistry, CO2 and oxygen and so on, and also DOC, which I'll briefly mention. So to think about the model biases and how biology or biogeochemical data can help, this is a figure from Paquita Zudema et al. Paper from BAMS, which was trying to look at the Eastern Ocean SST responses, and the main argument is focused on the Pacific and Atlantic Oceans, where there is a high correspondence between the SST biases and the precipitation biases, and the argument is that the ITCZ and the SST interaction produces coherent signals in the physics and couple their interactions here. And they just in passing say that the Indian Ocean shows no such correspondence, so the origin of the biases in the Indian Ocean must be coming from some other processes or somewhere else. And I think that kind of is the classic way we think about the seasonal cycles or climatologies and so on. We must always remember that there is an intraseasonal time scale here, which is integrating, the ocean is integrating it to give you a seasonal mean that really depends on the intraseasonal variability. So the years with more MJOs or fewer MJOs should have a different seasonal mean, and that's easily shown using a biogeochemistry model. You can show it in terms of the nutrient profile changes, primary productivity changes, barrier layer thickness changes, and so on. So the low frequency rectification of the physics by the intraseasonal oscillation is very critical in the Indian Ocean, especially because the mean SSTs are always close to convective thresholds. So even small changes at intraseasonal timescales are very critical, especially for the Bay of Bengal. So I'll say a little bit more about that in a minute. So coming back to the ocean forcing and the biogeochemical response, this is typically how the monsoon rainfall is always looked at. This is an El Nino year, and this is a La Nina year. And we always talk about 30 to 60 day or 20 to 60 day, depending on how you filter it. But you have these, so this is the climatological mean, and around that you have these active periods where there is large-scale rainfall over India, and there are break periods where it's drier. And you can see that the distribution changes. And typically in a wet period or a normal period, you would have more active periods than break periods, whereas the droughts come with longer break periods. The question of whether you really change the number of rainy days or you just change the rain in those rainy days, it still remains. And I think McFadden's question was about MJOs and mesos. So basically, the way to think about it on the ocean for me is that the MJO season typically goes from October to April, and then in May, June, when the land heating starts, there is a steering of these eastward propagating systems northward, which is what we call mesos. So I'll come back to that in the sense we have to also think of that in our biogeochemical response, because the mechanisms of what starts to steer them northward is still not understood. But recently, Lei, who is here, has published a couple of papers arguing that it's the horizontal gradient of the zonal wind. So the meridional gradient of the zonal winds and the barotropic instability that provides this steering mechanism, which is important also for the ocean response. In other words, this is typically looked at in terms of, let's say, the local Hadley cell, where you have subsidence over land during break periods and ascent over the ocean, whereas during the active periods, the local Hadley cell flips. So we can also think of the biogeochemical response at those time scales in terms of those processes. So this figure from Fritz Schart's paper is basically showing the winds and the thermocline depths from mean depths from SODA. So you can see that this is for January, June, August, and November. So obviously the reversal of winds is what we typically focus on. If you look at the thermocline depths, the summer season, there is obviously a wind stress curl. It's an evaporative basin here as opposed to this one, which is still very warm and gets as much rain as river flow. But you can see that the most dominant variability appears to be in the southwestern Indian Ocean, where you have the seasonal variability of the wind stress curl, which is pumping up and down the thermocline. This region is incredibly interesting because there is probably 70% of the moisture is being picked up here and transported across. But you also have the Indonesian through flow coming in and generating all kinds of remote forcing. So this region, which is very critical for the cyclone activity here, for example, and so on, is locally forced as well as remotely forced through Rossby waves and so on. So the biogeochemical and the ecosystem response is also most interesting here. But the interest in those responses here is basically in terms of the seasonal contrasts. What is creating the summer timescale, summer season variability in primary productivity, et cetera? What is the species composition, and what's happening in the winter? In the winter, you have dry continental winds coming, creating convection and deepening of the mix layer, whereas here you have very strong upwelling and mixing, plus the advection of nutrients off the coast. So a lot of the focus has been on the oxygen minimum zone, but there are several nice studies that have looked at the seasonal variability and intraannual variability and so on and so forth. So I'll come back to that, but basically in terms of integration, you can again imagine that you are not only connecting to the Southern Ocean with the deep and mid-level meridional overturning circulation bringing stuff from the Southern Ocean, but you also have the Arabian Sea and Bay of Bengal getting flushed on probably annual timescales. but we don't know how deep that goes, whether it's just the upper ocean or what is the connection to the deep ocean on longer time scales. So you can do the same across the equator. You have to consider the input from the Indonesian through flow and so on. So the idea of thinking about the biases and relating them to biogeochemical response is, if you think of an ocean model, when you do forced ocean model, you're typically prescribing the fluxes in some way, that it's interactive or fixed or whatever. And SSTs always look good, but the mean SSTs are high, so the errors are typically so small that you can easily blame them on the flux errors. You cannot attribute the errors to the ocean model, right? But if you look at the primary productivity, for example, then you have to explain that error in terms of the movement of the thermocline and the nonlinear rectification of the nutrients because of that movement. It doesn't work linearly like SST, flux damping, etc. So that's one thing that we have to remember. So if you do it correctly, then you can look at the errors in the thermocline, which you would typically compare, but the movement of the thermocline and primary production. So obviously you have to also be aware that your ecosystem biogeochemical models have all kinds of errors, but we can still get a good handle by looking at the integrated biogeochemical response, ecosystem response, to understand how the errors in the physics are being manifest in these responses. And I will come back to that a little bit more in the sense, even in terms of the stuff that's coming in and being flushed out by the meridional overturning in these two oceans, probably we can learn a lot by focusing on those things. Export production was briefly asked by somebody. I think the critical question is the Arabian Sea versus the Bay of Bengal. Bay of Bengal is obviously a very warm ocean, highly stratified, etc. But we don't have a real clue as to whether it's exporting similar amounts of carbon, for example, as compared to the Arabian Sea. The general idea is that the Bay of Bengal is full of eddies, and the Arabian Sea has got some eddy activity in this region, but this is from Vinu Valsala's paper, which has shown that if you look at AFC-CO2 fluxes, in fact, there is a very high coherence between the SSTs and AFC-CO2 fluxes. The strong upwelling here obviously brings some of the coldest waters, and the OMZ is on the other side. So you can look at other things, but we don't know exactly what is the contribution of these eddies to the mean production or the advection of nutrients from the upwelling zones into the center of the Arabian Sea. So we can look at that a little bit more carefully, and you can see that Takahashi data captures, obviously it's not too coarse to capture anything, but if you look carefully at the raw data, there is some indication that there is a mesoscale variability in the RC-CO2 fluxes. Coming back a little bit more specifically to the ITCZ, this is always kind of fascinating to me. I think Chirong Zhang has written a paper back in 2000 or so, which mentions that the Indian Ocean has a real double ITCZ, whereas in the Pacific it lasts just for a few months, but the models have this chronic double ITCZ problem because they are doing wind convergence as well as moisture convergence instead of doing just wind convergence. Over the Indian Ocean, it's interesting because during the boreal winter months, sun is to the south, ITCZ is to the south, but as the sun begins to move north in March, April, you can see that the ITCZ is held on to by the ocean because the SSTs are so warm. So it doesn't actually move across. So if you look at over the maritime continent, for example, you clearly see that the ITCZ crosses over the equator. You can look on the other side to the west, the same thing. So the onset of the monsoon is what we typically focus on, but this is the kind of the beginning of the steering of MJOs northward, etc. You can see that the crossing of the rain bands over the equator happens in March, April. So I suspect there is something here also in terms of physics that we haven't looked at very carefully. What comes to mind is things like the 30 to 70 day oscillations that John Kindle and Thomas had reported back in 1990s, which nobody has gone back and looked at. There are these features coming off of the tip of Madagascar and then propagating into the equatorial region. So those kind of things probably have something to do with this transition that happens. Plus, in the Indian Ocean, you have a very short seasonal equatorial undercurrent, which becomes much more strong during the typical Indian Ocean dipole mode. So we don't know exactly whether the equatorial undercurrent is being moved from slightly off the equator onto the equator and then the Wirtke jet, and how the biological response is happening at high frequencies on the Indian Ocean. Because that may matter in the sense during the Indian Ocean dipole years, the strong surface bloom, you have to understand whether it's a upwelled deep chlorophyll maximum or if it's the new species that are occurring at the surface and so on, which may also matter for fisheries and so on. The other thing that's getting a lot of attention, I think there's a poster by someone, Anika, on the warming pause and the role of the Indian Ocean. Obviously, the Indian Ocean is having this unique warming that's been going on for a while, which I think is also related to this flushing and the connection to the Southern Ocean. So this is from a paper by Roxy Matthew Cole, which looked at trends in the precipitation and SSTs and argued that that warming is concentrated on the Western Indian Ocean, and the stratification is creating a typical global warming response you would expect, where the increased stratification is reducing nutrient mixing and giving you a downward trend in the chlorophyll, which for the satellite period is shown here with SSTs. But on a longer time scale, you can always draw a line, but it's critical to figure out whether this is really a trend or if it's some sort of a regime shift, because this is, you can draw a line there and a line there. And many in India believe that there is a 60-year time scale, there's a 20-year time scale, and then there's a 60-year time scale in rainfall. It's only 5 minutes? Okay. So that has to be figured out. But in terms of why the Indian Ocean is warming, we must remember that the Southern Ocean is, because it's a channel, is forced very strongly by the winds. The wind, Ekman forcing can go basically to the bottom, where bottom drag becomes a limiting issue rather than thermocline and so on. So the warming is also very rapid and is penetrating pretty deep in the Southern Ocean. And this warm water is being pumped into the Indian Ocean at deeper levels and the mid levels. And the thermocline theories would tell you that if you change the temperature of the deep ocean, then the upper ocean has to respond. Okay, if you warm the deep ocean, then the upper ocean thermocline has to become deeper to balance the heat uptake via the surface. So that could explain why you are having a unique warming in the Indian Ocean. We haven't looked at that very carefully. Okay? And just to mention models again, this is just one of the models which seems to capture the long-term trends in SST and chlorophyll. But again, is that a regime shift or is that a trend? We cannot say very clearly in the model. But I should mention that there are a couple of papers showing that the CIMI-5 models basically are not doing the trend in the monsoon properly, and their projection for the future is dynamically inconsistent, basically because of the impacts of aerosols as far as we know. So talking about aerosols, here is the pattern of SST warming. This is for 1950 to 2015. This is just the last few decades. And Roxy's focus is here. He's arguing that this is where the stratification is increasing and the chlorophyll response is very strong. But the Arabian Sea is warming much faster than the Bay of Bengal. Prasanna Kumar wrote a paper arguing that the Bay of Bengal is not warming because the cyclones and depressions are increasing, I think. But actually, it should be the other way. Because the Bay of Bengal is already so warm near the convective threshold, it cannot warm anymore. If you try to warm it, it has to get rid of the energy by basically convecting more, which means we have to figure out what is the biogeochemical and ecosystem response that's associated with that. But this ocean can warm rapidly on the other hand because it's still much below convective threshold on the annual mean. And I think that is already happening, and Roxy has now another paper coming out this week or next week in Nature Communications showing that there is no direct relation between extreme rainfall events and heating here, but there is a remote forcing. So this warming is pumping in moisture. So the floods they had in Bombay last week or 2 weeks ago and the large-scale floods that have been recurring in northwest India are basically related to extra moisture supply coming from here. So even though the depressions are decreasing here, the pumping of moisture from here is increasing. So that may have something to do with the kind of things that Joachim had reported on noctilucas and so on. So we have to look more carefully as to what the biogeochemical response has been here. Joachim had his own theories which got hammered, but you cannot distract Joachim. Where is he? Is he here? He couldn't be here? Okay. So I'm wasting my energy? So anyway, I think the patterns, even though the Indian Ocean is warming overall, the patterns of warming will matter. For example, the equatorial region is how is this related to the Walker cell? How does it affect the local Hadley cell? And what does it mean for the biology? So just to put more emphasis on the meridional overturning, this I took from Jay McCreary, or one of his talks he gave in India, which is showing, this is basically corrected for the Indonesian through flow and showing the deep cell, the shallow shell, and his favorite cross-equatorial cell that Peter mentioned briefly. So the Indian Ocean, because it's close to the north, the water that's coming in has to get converted to surface water somehow and come back out. So this integration of the physics by the biology is something should yield a lot of interesting information. Maybe Laura is going to get more into that in her ventilation talk, but I found one nice figure from Dennis Hansel. I should have put his name here. I think this is from a chapter in the book that you guys edited, which is showing DOC. This is the only biogeochemical figure I found other than the anthropogenic CO2 stuff, which kind of tried to argue for all the source waters for the DOC. Dissolved organic carbon is a very interesting tracer that we should, if we make proper measurements, can provide a lot of information. Basically, a percentage of it remains in the surface as a part of the net community production, and then what gets transported out and remineralized, et cetera, depends on mixing and meridional overturning, et cetera. So warming and stratification and enhanced mixing due to cyclones and so on should give us some sense of using the DOC budget to say what's happening to the physics in terms of, or how the DOC is being, is an integrated signal of the physics. So that can work on all time scales. So this multi-decadal time scale of the connection to the subantarctic mode water or southeastern subantarctic mode water, subtropical underwater, and so on. There is a very strong ventilation zone here, for example. So I think the natural flushing time scale of the Indian Ocean for the entire MOC is probably around, from the models you can estimate it's probably around 30 or 50 years. And I think the global warming is basically modulating this flushing time scale. So that should be somehow being able to extract, we can extract that using these biogeochemical tracers, which would be very interesting because that's the only way to say something about what the vertical mixing may be doing wrong in the models and what the heat content variability could be missing in terms of the global warming pause and so on. For example, the ideas are that now the Indonesian through flow is putting heat into the Indian Ocean, which is what partly keeping the heat hidden away from the atmosphere. Just to go out on a shopping list, this is also the figure that Roxy used to argue that it's not just the chlorophyll that's been going down in the Indian Ocean, that when you account for fishing efforts and so on, there is probably also some sort of a drop that has happened in the tuna. I don't know whether it's recovering, but in Big Eye, the effort has gone up. I don't know if that's been removed here, but overall the tuna has at least flattened out. So Indian Ocean started to get exploited more recently by all the international tuna eaters, but you know that there is lots of productivity there, but we don't know how this is changing. And we know basically nothing about the disease pressure. Is somebody giving me an indication of time or is it random clink? How much?
1 minute, 25 minutes.
Okay, so I'll wrap up soon. So I don't know, IIOE is probably not going to get there, but hopefully IIOE provides a platform on which things can grow, including diseases, right? So this I put as backup slides, but once I was given a few more minutes, I'm going to use them. So the other things we should look at in terms of the physics and biogeochemistry interacting is the things like N-star. I think everybody knows this is basically a combination of nitrate and phosphate. That's a very good measure for nitrogen fixation and denitrification. So Indian and Pacific Oceans, in fact, act as a massive sink for nitrate in terms of denitrification. I don't know if this is all nitrogen fixation, but nobody knows. So that's an interesting question that needs to be figured out, especially in terms of what is coming in through the Indonesian through flow, which is also not something we know very much about. So when I look at the Indian Ocean, it looks like we should be able to observe these connections and then get a very nice integrated picture of everything, including heat budget, mass budget, DOC, and so on and so forth. This is just sections of the N-star, also from, I think this is from Dennis Hansel's paper also, or book chapter, which is showing sections in the Arabian Sea, Central Indian Ocean, and the Bay of Bengal. And you can see the impact of the apparent oxygen utilization on things like N-star. You can do that in DOC as well. Obviously, denitrification signal. So contrasting these more carefully should tell us more about the question that was being asked about the oxygen minimum zone contrasts in the Arabian Sea and the Bay of Bengal. So I think the unique configuration will offer us lots of very nice integrative ideas on connecting physics and biogeochemistry and ecosystems. This is just the anthropogenic stuff. This is from probably Dick Feely and Chris Sabine's work. I should have put that somewhere there. I won't say much about it. Should I leave some time for questions? Yeah, you could. Okay, so maybe I'll stop there and take any questions.
Thank you, Raghu. We have time for a couple questions.
No questions.
I wanted to ask about the using DOC as a tracer. Do you mean only amounts, or do you also mean type and content? And
yeah,
using DOC as a tracer for what's removed and how you can know how water moves based on what was pulled out.
You have to basically do a budget to see net community production, what remains in the surface, and what is being mixed and MOC. So it's the challenge for me will be to separate the mixing versus the MOC advection.
Okay.
So what is local and what is being brought in?
So it's amount.
It's a full budget.
Yeah.
Thank you, Raghu. So I wanted to ask you a question about the SST increase in the Indian Ocean. You talked about the mechanism being coupled to the Southern Ocean. Can you contrast that with the other two basins just so I can get my head around it?
Yeah, so in the Pacific Ocean, it's a much bigger ocean, much wider ocean, and the pathways are much more complicated. And the Pacific has no northern boundary all the way to the Arctic, so it doesn't have to come back out at the same time scale. So the Indian Ocean time scale is much, much faster, right? The Atlantic is obviously very different because it's bringing in water from the north. So I think the Indian Ocean is very unique in the sense it can take, Southern Ocean is unique, but the Indian Ocean linked to the Southern Ocean is also unique. So that link is much faster, I think. But the more interesting thing for me would be the thermocline response to deep ocean warming. So you don't necessarily need the MOC to do everything, but we don't understand the mechanism of how the upper ocean responds to the heating at the bottom. So Bucoletti and Philander and Fedorov had done some work on it based on idealized modeling, but nobody has looked at it. I think maybe Caroline, is Caroline here? I think she's trying to look at some of this stuff, but I'm not sure. But that has to be looked at, yeah.